Good day, everyone. Happy to have you here with me. I'm Aaron Moulin, one of the field application scientists in North America for Purolite. And today we're going to talk about some advances we have in protein A chromatography resins. So on the agenda today, we will have an overview of our patented jetting technology. After that, we will talk about the Presto Jetted A50, including some highlighting points about process intensification. And then we will give you a more detailed introduction to our Presto Jetted A50 HipH resin. So first, we will start off by talking about some jetting technology. But before we talk about jetting technology, I'd like to talk about the traditional way to produce agarose beads, which is via batch emulsification. So let's start here. Everyone starts making agarose beads in the same way and in the same place with agarose extracted from red seaweed. Everyone does it this way. You take your agarose, you solubilize it in hot aqueous media, hot water. And after that, you put it into a large tank for emulsification. Inside that tank, you also add a large amount of solvent, typical nonpolar aprotic solvent, toluene in most cases. Inside that tank, you have an impeller. The speed at which you turn that impeller and the length of time for which you turn it will determine your mean bead size and your bead size distribution. So after you've done this, you let it cool. You then chemically cross-link the beads, usually with epichlorohydrin. Nearly everyone uses epichlorohydrin. You do this to make sure that the beads are chemically and physically stable. So for instance, if you didn't chemically cross-link them, if you introduce certain chemical agents, particularly chaotropes, you might then melt the beads and make a gel out of them. So for instance, if you ran guanidine or urea over a non-cross-linked bead, you could melt it. After chemical cross-linking, you then screen the beads. And when I say screen, I don't mean put it on your ACTA and test out conditions. I mean physically screen the beads. So you use large metal sieves. Usually there are two. One that retains very large particles, one that lets very small particles pass through, and you keep what's in the middle. So these are usually, as I said, very large metal sieves. You put them into mechanical agitators that shake them and let the beads pass through. This will account in the end for about 50% of the total processing time of making a bead. After the screening, you functionalize the bead. So in this case, we've made a Q resin. We have a Q group at the end here. After functionalization, you then do all of your testing. So you'll take that Q resin that you just made, make sure it has the appropriate total ionic capacity, make sure that the retention time for alpha chymotrypsinogen or whatever your other test molecule is appropriate for the resin. From here to here, so from front to back, that takes about 6 to 8 weeks, depending on the nature of the bead that you're making, which means by turn that about 3 to 4 weeks of that time is spent in this physical screening process. How does jetting work? From a physical standpoint, it works very similarly in that you have aqueously solubilized agarose, you have some sort of nonpolar aprotic solvent, you mix it together and you get beads. In this case, you'll notice that there is no emulsification tank, there's no impeller. Also in this case, this nonpolar aprotic solvent is food-grade mineral oil. So what's happening here is you have your aqueous agarose being pushed into your food-grade mineral oil, but instead of there being an impeller, you have what we term the agarose in a membrane can. So the membrane can is half what it sounds like. It does sort of look like a can, maybe about half the size of a soup can, and it's full of thousands of laser-etched holes. So what's happening is you're pushing the agarose out through those holes into the food-grade mineral oil. So the particle size is determined by the size of that nozzle and the size of the holes, the nozzle being the membrane can, the flow velocity of the agarose through that, the viscosity and the surface tension, I think largely in part driven by the agarose percentage, and then the frequency of the nozzle. Frequency, you'll see that it says shaker here. When you see this in real life, it sort of looks like a very large paint can with a sonicator probe stuck into it. When you get up close to it, you can see that that probe is moving very, very fast. So what you have is the agarose being extruded through the membrane can while it's moving at a very specific oscillation frequency. So you get the drops extruded into the solution and they're sort of chopped off by the motion of the membrane can. So all of these together will determine the size of the bead. There's no impeller, there's no emulsification tank. You can see here, maybe you've sort of latched onto the idea that this process can essentially be continuous as long as you keep supplying agarose and keep supplying mineral oil, you keep making beads. You're not limited by the size of an emulsification tank. What we are limited in a practical world is the size of the collection vessel. So currently we collect 600-liter batches, but if we chose to collect more, we could collect more. The notable thing, no emulsification, no impeller, so there's no need for that sieving step that accounts for about half the time of total production. So you can make a jetted bead in about half the amount of time as you can an emulsified bead. So it's faster. Are there any other benefits? Well, you can see here, there's an obvious physical benefit immediately. So batch emulsification versus jetting, so impeller versus the can. If you look at a typical batch emulsified product, this is the end product. This is what you get after doing your screening from a batch emulsification process. And you can see that many of the beads here are roughly the same size. These beads are all somewhere around 90 microns. But you can see there are also a significant number of beads that are much larger, like these are at least twice the size, and then also a significant number of beads that are much smaller, well less than half the size. If you then do a plot of the mean bead diameter versus the number of beads that have that diameter, you'll notice that that plot is relatively flat. You can see that there's sort of hard cutoffs here, and those correspond to the sieving sizes. Essentially, you don't get beads smaller than a certain size, and you don't get beads larger than a certain size. But if you look at the jetted bead here, you can see there is still a distribution, but this distribution is much narrower. Some beads are smaller than others, but on the whole, all the beads are much closer in size. So if you look at that same plot of mean bead diameter versus number of beads, you'll see that there's an obvious centroid in that plot, which is lacking in the batch emulsified plot. So physically, these beads do look different in terms of their distribution. Let's talk a little bit about Jetted A50. So Jetted A50 is our flagship Protein A product. It's on a 50 micron jetted bead, hence the Jetted A50. It is high capacity, stable to caustic, and has good binding to fabs of the VH3 family. So you'll notice here one of the sort of hallmarks of a jetted resin is that they tend to have rapid uptake and then plateau relatively quickly in terms of dynamic binding capacity. So you see that here both with this polyclonal IgG and this IgG1. Especially with the IgG1, you see that there's rapid uptake and then it plateaus relatively quickly. So at low residence times, you definitely get a mass transfer benefit with a jetted bead. And again, that's almost entirely driven by the uniformity of the bead size. You don't have to wait for molecules to diffuse through a very large bead to achieve maximal binding capacity. So, of course, if you let this go out long enough, they approach each other as you get to longer residence times, but certainly at short residence times, jetted beads will almost always outperform batch emulsified beads in terms of dynamic binding capacity. Some pressure flow diagrams here. So let's sort of focus on this 20 centimeter bed height because it's very popular out in the industry. So if you want to pack at a 20 centimeter bed height and stay below sort of that 1.8 bar safety limit, your max linear velocity will be somewhere around 200 centimeters per hour. Of course, if you have the ability to have shorter bed heights, you can achieve much faster flow rates at that same sort of pressure drop. This is another way of sort of showing the same data. So we're looking here at a boundary curve, a safety boundary curve of linear velocity and bed height. And then these sort of would-be isotherms are just showing you different residence times. So again, at that sort of 6-minute residence time, you notice here it's in sort of a lightish blue color. That 6-minute residence time, again, we cross at the safety boundary at 20 centimeters and 200 centimeters per hour. Again, if you have the ability to have shorter bed heights, you can operate much faster. So 2 or 4 minute residence times, depending on how short you're able to go with your bed height. And we call this our smart cycling regime, where you have shorter bed heights, faster flows. So speaking of smart cycling, this slide is showing the essentially 4 strategies that we envision as being part of our smart cycling regime. Those 4 strategies are designed to take advantage of the superior mass transfer qualities that you will see with a jetted bead with a more uniform-like bead. So for instance, here we have our standard column. Maybe it's a 300 by 20 centimeter column. The first strategy would be simply reduce the bed height, maybe reduce it by half. You would reduce the bed height with a concomitant increase in flow. So if you reduce by half, in general, you could increase the flow by 2. So you'll process the same amount of material in the same amount of time, but you will use less resin, so you will have less cost and increased productivity. Productivity should go up by about 2 times, right? The second strategy would be to reduce the bed height and the column diameter. This would also be with a concomitant increase in flow. This one will usually see a somewhat longer processing time than the original. Here should see the same sort of processing time as your standard column. Here it might increase because you might not be able to achieve a fast enough flow to make up for the reduction in height and diameter, but this will increase productivity and cost savings even more than just reducing the bed height. The third strategy would be what we call dual flow non-loading steps, meaning you have your column, perhaps it's a standard size column, or maybe it's a column of reduced bed height or reduced bed height and column ID, but you will load at your standard loading flow rate, which maybe is slower, but then all the non-loading steps will be faster. So you would do some experiments to optimize the speed at which you can run all of your non-loading steps so that you save time and money in resin costs and also in buffer consumption, buffer costs. This one also may or may not have longer processing time than your standard column, probably won't. The fourth strategy would be dual flow in the loading phase, meaning that your initial part of your loading phase will be fast. Maybe you load at a 4-minute residence time for the first part of your loading phase. Do that for perhaps 80% of the total load volume. Then the last 20% of the load volume, you would slow down, maybe go from a 4-minute residence time to a 6-minute residence time to sort of catch all the rest of it that you can. I always use the analogy of loading your gas tank when you're at the pump. So you might pump really fast at the beginning, but then many of us I know have slowed down that last little bit to top up the tank. Similar idea here, go very fast at the beginning, then slow down. So again, these 4 strategies, either one at a time or in various combinations, are what we call smart cycling. And I'm quite sure that we will have another webinar in the future discussing this in more detail. We have a lot of modeling data around this, and you should look forward to that in the future. So let's look at some information about process cycling lifetimes, as the slide says. These slides are a little information dense, so let me sort of walk you through what we're seeing here before I start talking about the actual data. So I'm going to start with these 2 lines. The green line that you see here is 80% of the initial dynamic binding capacity, so 80% of the initial QB10. This sort of dark blue purple line is the 90% yield barrier. So that's what we're looking at with these 2 lines. The red dots are actual yield percentages across all of these cycles. And then the blue dots are dynamic binding capacity every 10th cycle. So you can see here that in this particular cleaning regime, with loading of about 51 mg per mil at a 3-minute residence time at 80% the initial QB10, you are cleaning with a 0.1 molar sodium hydroxide for a 60-minute contact time. After 150 cycles, we're still well above both the 90% yield line and the 80% initial QB10 line. So in this sort of loading, residence time, cleaning regimen, we get well more than 150 cycles out of Presto Jetted A50. So we're looking at the exact same graph here. The only differences are the loading. We have a higher loading, so we're at 91% of the initial QB10. We have a 12-minute residence time here, and then this cleaning strategy has changed. We have 0.1 molar hydroxide for a 75-minute contact time. You can see that out to where we have the data, which is about 125 cycles, we are mostly above the 90% yield line. We had a couple excursions to the line or slightly below, but in general, we're still above that 90% yield, and we're well above. In this case, it looks like we're plotting at the 85 or 86% QB10, but we're well above both of those lines in this particular cleaning regime. One more, so we're looking at a very similar sort of graph. So you can see that at another 91% of the QB10, 12-minute residence time, and this time 0.3 molar hydroxide for a 15-minute contact time. Out until about 105, we're still above the 90% yield, and we're still well above what looks here, again, to be maybe an 86, 87% QB10 we're looking at here. So very good platforming, very good cycling resin. You can use it in all of these instances for well more than 100 cycles. I should say, all of these are different experiments that we did, 60-minute contact time at 0.1 molar, 75-minute contact time at 0.1 1 molar, and then 50-minute contact time at 0.3 molar. I would say none of these exactly are official recommendations from us. They are sort of testing strategies to see what we can do with the resin. Our official recommendation to start would be to do a 0.1 molar cleaning solution with a 15-minute contact time every cycle. And then if you find you need more aggressive cleaning, you could either up the molarity every 10th cycle or so, so do 0.1 molar for 9 cycles, and then maybe 0.2 every 10th cycle, 0.3 if you had to, or you could, of course, increase the contact time, combination of some of these strategies. But again, our official recommendation would be to start with 0.1 normal and 15-minute contact time every cycle, and then adjust as necessary from there. Let's talk about some of the other attributes here. So leached protein A, you can see that in terms of parts per million, the leached protein A is relatively nominal, not anything outside of what you would expect. There is a little bit of a spike here at cycle 50, but it's relatively flat across the board out to 100 cycles. And you can see that host cell protein removal from CHO is also excellent across all 100 cycles in this particular study. Let's talk a little bit about Jetted A50 HipH. So this is our newest and unique offering to the market in terms of protein A purification. So we listen to the voice of the customer out in the market, and as everyone knows, we're starting to see more and more antibody-like constructs that are moving away from the traditional monoclonal antibody, be those fragments, single-chain FEs, diabodies, multispecifics, bispecifics, or fusion proteins. Many of these proteins and protein constructs are sensitive to acid, be that because they aggregate at low pH or because they have some sort of acid lability. So it was desirous in the market to have a resin that would allow you to elute at pHs, at higher pHs, where you didn't have to spend so much time at low pH and potentially suffer from a lot of aggregation or a lot of acid lability, acid cleavage of these constructs. So we developed the Jetted A50 HipH resin. This was done in collaboration with Repligen and Navigo. They developed and supply us this ligand. So a traditional protein A ligand, protein A is a 5 subdomain protein expressed in staph A. Usually you would take one of these subdomains, you would mutate it, try to get the beneficial qualities that you want, multimerize it, put it onto a bead. That's not how it works for the NGL Impact A high pH ligand, as it is called. Instead, what we have are these shuffled monomers, as it's called. They're not exactly A domain, they're not exactly B domain, they're not exactly Z domain. They're a little bit of all of them shuffled together. And then you screen these shuffled monomers for your desired criteria. In this case, we wanted hydroxide stability, specificity for FC regions, and elution somewhere around pH 5.0. And of course, we wanted to retain good capacity. So after shuffling these monomers, you identify the ones that initially meet these criteria. Then you further optimize those by some sort of site-directed mutagenesis or other techniques. You have your modified variants. Once you've identified the one that performs the way you really want it to, you multimerize that and attach it to your bead. And that's how we developed the Jetted A50 HipH using the NGL Impact A high pH ligand. So again, you'll see here's some dynamic binding capacity data. So we're looking again at Presto Jetted A50 as a sort of benchmark in our hands of a 50 micron bead, competitor A, and then Jetted A50 HipH. So you see the Jetted A50 HipH still retains that benefit in mass transfer that at low resonance times you have rapid uptake and fast plateauing. It doesn't have quite the capacity that Jetted A50 does, but it still has very good antibody capacity by traditional standards. We're still seeing around 60 grams per liter binding capacity at a 6-minute resonance time. And you approach that very quickly. So it's still very, very good at low resonance times, much like its predecessor, Jetted A50. Let's look at this slide in sort of two halves here. So let's focus initially on this half of the slide. When we were trying to optimize the Jetted A50 HipH, we did some experiments here. So what you're looking at here is the same pH gradient run with 4 different resins. A competitor resin, Jetted A50, both of these are sort of traditional protein A resins, and then 2 late-stage prototypes of Jetted A50 HipH, HipH 002 and HipH 001. So you can see in this pH gradient with Jetted A50 and competitor B, the traditional protein A resins, you get elution of of the FC fusion protein about where you would expect, around pH 3.5, 3.4. You need to get down into that sort of acidic realm to elute off that. But you can see that with the two late stage prototypes, you could elute at much higher pHs, pH 5.2 and 4.8 respectively for 001 and 002. Of course, you could use these to elute at very low pH if you chose to, they would elute. But the real take-home message here is that you have a much wider range of pH available to you at which this FC fusion construct will indeed elute from this resin, the highest being apparently right here, 5.2. Let's focus on the right-hand side. You're seeing something very similar. We're running the same sort of pH gradient, but then we're just doing a scatter plot of the same 4 resins with 5 different monoclonal antibodies and where they elute. So again, you can see for Jetted A50 and competitor B, the two traditional protein A resins, you get elution down around pH 3.5, where you would expect to start seeing elution. But for the two late-stage prototypes of high pH, you see that for several of the constructs, several of the MABs, you can elute at much higher pHs, 4.0 or higher. In particular, with a high pH 002, you can elute at 4.5 or maybe slightly higher with 4 out of the 5, and above 4 with all 5 of them. You'll notice that with high pH 001, you do need to get into lower pHs with these two. I will say that these 3 monoclonal antibodies have a VH3 lineage. So what we think we're seeing here is some VH3 binding that requires lower pH to affect total elution. I will say that high pH 002 is the actual commercialized version of this. So when you buy Jetted A50 high pH, you are getting this late stage prototype 002, which demonstrates this high eluting pH behavior across all of these antibodies. And based on some of these data here that you're seeing and other data that I don't have included in here immediately, we believe this to be a more sort of a pure FC binder without the VH3 binding properties of some of the other protein A resins. So what we're looking at here is another experiment with 2 different antibodies trying to elute at different pHs. So we're eluting at 5 different pHs here, 3, 3.5, 4.0, 4.5, and 5.0. What you're seeing here then is a bar plot with MAB3 with Presto Jetted A50 high pH, that's in the blue, MAB2 as we call it with Presto Jetted A50 high pH, and then again MAB3 with Presto Jetted A50 in the green. So this one is included here as sort of a negative control. There's no secret sauce here in terms of the Jetted A50. We just wanted to include something that was a more traditional protein A resin. So we would expect any traditional protein A resin to show similar behavior. Take home message here, Jetted A50 high pH is able to elute these 2 monoclonal antibodies at all 5 of these pHs, even up to pH 5, whereas you see with a more traditional protein A resin, in this case the Jetted A50, sorry, you start to see difficulties in recovery once you get above pH 4.0, which is exactly what you would expect from a traditional protein A resin. It doesn't elute very well once you get above pH 4. What about some of the other performance data here? So let's look at the column volumes. This is column volumes in regards to the experiment I just showed you on the previous slide. So you can see here that with Jetted A50 high pH, same color coding scheme, both of these monoclonal antibodies, MAB2 and MAB3, are able to elute off that resin at 2 column volumes or less, even up to pH 4.5. Once you get to pH 5.0, you are talking slightly more than 2 for one of them and just over 3 for another. But with Jetted A50, a traditional protein A resin, once you get above pH 4, it takes 6 or more column volumes to be able to affect elution off that resin. So not only do you get elution at high pH, but you still get very efficient and effective elution in relatively small column volumes. Protein A leakage is relatively stable across all 5 of those pHs, certainly in the pH ranges where we envision that it would be used most, between 3.5 and 4.5. It is nominal. We do see some higher leakage at lower pH, which is to be expected. There seems to be something feed specific going on with MAB2 here, possibly some protease behavior. But in general, we see pretty nominal protein A leakage. I would be remiss if I didn't say that there is a specific ligand ELISA kit for the NGL Impact A high pH ligand available from Repligen. We do, of course, recommend that you use this specific kit. If you use a more generic protein A detection ligand kit, you will likely get erroneous results. So you can get this specific ligand from Repligen. You can also get the NGL Impact A, the Jetted A50 ligand from Repligen in a testing kit. Let's look at a lifetime study. So we are going to look at a 73% load, 73% of the initial QP10 load flows at 4-minute residence time. And this cleaning regime here, I will note that this is not an official recommendation from me or from Purolite. This is how this study was done. My official recommendation would be start with 0.1 normal hydroxide every cycle and increase the hydroxide concentration every 10th cycle if necessary. But this study was done with 0.1 normal every cycle, then 0.5 every 10th cycle. So you can see after 200 cycles, the yield is still above 80%, very good yield after 200 cycles. You can see the percentage of the initial DBC10 does start to tail off after about 100 cycles, but even after 200 cycles, we're still at 80% of the initial QB10, so we're above our 73% safety factor, so we're not losing anything. You can see that the host cell protein removal is flat across all 200 cycles. We're still getting very good HCP removal even after 200 cycles. And the monomer content as analyzed by size exclusion chromatography is also flat across 200 cycles. So again, a very good cycling, very good performing resin. Let's look at a very specific case study. So here we have some data that we did in collaboration with Alvotech, where we're eluting the same fusion protein at multiple different pHs. So a little difficult to read here. I'll walk you through it. We are eluting at pH 3.5, 3.8, 4.0, 4.2, 4.5, 4.8, 5.0, and then also 5.3. So you can see the exact same method was run. The only thing that's different is the elution pHs, and up to pH 4.5, these chromatograms are essentially superimposable. You can see there's essentially no difference in elution at pH 3.5 versus pH 4.5. You do start to see some tailing when you get to 4.8, and that strip peak gets a little larger. That gets more pronounced at pH 5, and of course at 5.3, they had to put in an early regeneration step. When you look here at the elution CVs, you can see that's reflected here up to the pH 4.5. The elution CV was 1.76, so still really good. The elute pH tracks where we'd expect it to. Their platform protein A yields are typically greater than 90%. They were seeing very similar to this until they hit about pH 4.8, where they started to see that peak tailing. What do the rest of the quality attributes look like? So you can see that the purity across all of these pHs looks excellent. This is monitored by monomer content via size exclusion. HCP clearance is also excellent. It looks as though there might be a trend here that the clearance gets better as pH goes up, but I will point you to the axes scale. So we're talking about 3.2 log to 3.5 log. So is this really a trend? Maybe, maybe not. It's hard to say. It might be within the error bars. More study needs to be done on this, but certainly it remains good across all the cycles, if not improving. And the DNA content, as you can see here, after pH 4.0 really starts to tail off. So there seems to be definitely a benefit to eluting at high pH when it comes to CHO DNA in the sample. So Alvotech, based on these data, has sort of identified 4.5 as being a sweet spot to start with, because they got very good results, at least for this FC fusion protein. And they are certainly doing some more studies around this to optimize. So in summary, we now have from Purolite available a toolbox of 2 Jetted A50 resins, our traditional Jetted A50, and now our new Jetted A50 HipH. So our Jetted A50 resin is designed for purification, your general purification of all monoclonal antibodies, high capacity, high performance, caustic stable. Now we have the new to the market and unique to the market Jetted A50 HipH, which is specifically designed for pH sensitive antibody based therapeutics. It's high capacity, hydroxide resistant, suitable as a platform for anything that contains FCs, so be those MABs, fragments, fusions. Get excellent recovery and quality, as I've shown you, across a wide range of elution pHs. As we showed from some of that data that we did in collaboration with Alvatech, it offers the potential to improve impurity clearance on protein A capture, and also could have beneficial effects on other downstream steps in terms of easing the requirements needed to affect those downstream steps in terms of aggregate clearance, DNA clearance, etc. Of course, I would be remiss if I didn't say that we have all of our resins available pre-packed in any format that you can get from Repligen. We collaborate very heavily with Repligen, not only on our ligands, as I described before, but also with our pre-packed columns. So anything you can get from them, you can get our resin in. And of course, I would like to thank you for your time.
Hi, everyone. Thank you very much for listening. So I'd just like to introduce Aaron to the live Q&A. So hoping that we've got some audio and that everything is working okay. Aaron, can you hear us okay?
I hear you just fine. Can you hear me?
Yes, excellent. Super stuff. So yeah, so we'll just run through a few of the pre-submitted questions that we've had from the registrants for the last couple of weeks, and then we should hopefully have a bit more time towards the end of the session to go through any questions that we might have missed as well. So is there any change in porosity between jetted and batch emulsified beads?
Okay, yeah, let me answer this question. First, I'll answer it by saying a couple things about porosity with beads. The porosity is not a release criterion. We don't explicitly measure the porosity. What we do is monitor the apparent porosity, mostly by retention times, so apparent KAVs for the resins, much has been described in the literature about how to do this. That being said, we don't see any observable difference between jetted and batch emulsified beads in terms of this sort of testing, retention times, KAVs, those sorts of things. So hopefully that answers that question. So far as we can tell, the porosity seems to be more a property of the agarose itself and the percentage of it, rather than how the bead was formed explicitly by emulsification or jetting.
Excellent, thank you. So can Jetted A50 HipH be used for antibodies that aren't sensitive to low pH elution? Are there any benefits?
So yeah, a good question. I touched on this briefly in some of the slides in the presentation. The answer is yes. It can be used for any antibody that you would choose to use it for, even ones that aren't sensitive to low pH. Are there any benefits? Well, that will depend on the antibody itself. We have seen with some of our customers that there is a palpable benefit to using high pH with antibodies that are prone to aggregation, be it at low pH or any pH, especially antibodies that seem to have a lot of aggregate already present in the feed. Using a pH gradient with high pH has been able to nearly baseline separate high molecular weight species from monomeric content using high pH in a way that traditional protein A's haven't been as successful at. That's one of the main ones that I can think of. Of course, I touched on a little bit too that there seems to be potentially a trend that HCP clearance is variable at different pHs. I showed you one set of data there with, I believe it was the FC fusion protein. Alvatech also has another set of data with an IgG2 that shows a similar sort of trend with a much larger change in the log scale. So it goes, I believe, from 1.5 to 3.6 or so. So that one seems like it's actually very real as you increase the pH. So aggregate removal potentially helping to mitigate some problematic HCP clearance issues. These are things that are certainly worth testing with high pH because you have a much wider range of pH that isn't available to you with the traditional protein A that might help with some of these. Is there a guarantee that it will? No, of course not. But it certainly gives you more options to try than with a traditional protein A where you're kind of limited between 3 and 3.7 at the sort of the upside.
So can I use standard buffer systems with Jetted A50 HipH?
So sure, yeah. In terms of chemical compatibility, all the standard buffer systems that you're using will be compatible with high pH. Of course, you just need to keep in mind the chemistry. Do you want to use citrate at pH 4.7? Probably not, because the buffering capacity is not great. But certainly acetate is probably the best suited buffer to use with Jetted A50 high pH due to its pKa being around 4.5. So you have really good buffering capacity in the pH 4 to 5 range with acetate. But of course, you could use citrate. Glycine is probably not a great choice as you won't have really good buffering capacity above 3 point something right? But everything else you should be able to use. I did see in, I'll take a chance to answer it now. Someone asked in the chat, should you stay away from things at pH 5.5, for instance? And the answer to that is possibly. It will depend on the feed streams, of course. We do have some data not shown in the presentation here that when you're up around pH 6, you can see a significant amount of leakage of product in washes at pH 6. For instance, that a lot of that can be mitigated by adding salt. So we were able to mitigate almost all of that by adding 1 molar salt to the wash buffer. But yeah, if you're going to use buffer systems, especially washes at lower pH values between 5.5 and 6, you might want to evaluate those for use with high pH, because you might see some reduction in recovery due to washing off some of the bound antibody. And of course, the person who asked that question is driving at a fair point. This ligand was designed to elute at higher pHs, so maybe it's not surprising that things around, between 5 and 6 might show some elution. But beyond that, from a chemical standpoint, everything should be compatible. You just need to make sure that you would choose appropriately for your correct buffer system. And you'll have to do some testing, because this won't behave exactly as a traditional protein A has behaved in the past.
Excellent answer. Thank you, Aaron. Okay, so do you have any viral clearance data?
This is an excellent question. The answer to that is right at the moment, no. But we are in collaboration with one of the customers out in the field generating these data right now. It's happening right now, both for Jetted A50 and Jetted A50 HipH. So we will have a full viral clearance data set for both weapons in the not distant future. So those things are happening right now as we speak, or as I speak.
Excellent, thank you. Okay, I think. Oh, one more we have. So does it have any more bonding for the VH3 domain?
I sort of alluded to this in one of the slides. Yes. It has minimal binding to to VH3 domains. We don't have the sort of data that you might see with some of the other protein A resins, delineating all the different isotypes of VH3 and which ones do and which ones don't bind. In general, it binds VH3 very poorly. That's high pH. Jetted A50, regular Jetted A50 binds VH3 very well. Jetted A50 HipH binds VH3 very poorly, if at all. And we have some anecdotal evidence, including some of this salt mitigation in elution, pointing to it being mostly FC driven with very little and poor VH3 binding. So if you're looking to bind VH3 antibodies specifically, or VH3 containing Fab fragments, high pH is probably not the best choice going forward. So it's similar to some of the other competitors on the market in terms of its reduced VH3 binding quality.
So thank you. Okay. Super. So I think that's the end of the pre-submitted questions. I just want to allow any of the other attendees to use the questions feature if they have any other questions for Aaron. We'll hold on for a few more seconds. But if not, please, feel free to. I think you've got both of our email addresses. So if there is something that pops up after the presentation, we'd be more than happy to reach out to you and get those questions answered. So we'll give you a few more minutes, or a few seconds.
While we're looking, I'm going to answer one of these right now. Is the jetted process GMP? Yes, our manufacturing facilities are GMP. We have the traditional sort of host of ISO certifications for those, 9001. I don't know all of them off the top of my head, but if you need those, you can contact us in the quality department at Purelight can supply all of those to you. But the answer is yes. So these beads are for GMP use and manufactured appropriately. And we do make batch emulsified beads as well in the past. So both of our processes are GMP.
Excellent. No, thank you very much. I think that'll probably conclude it today for us for the webinar. So just want to say a really quick thank you for all of your questions and for everybody that attended today's session. As a follow-up, you'll shortly be receiving an email that provides you with access to the on-demand version of this presentation, which also includes the live Q&A that we just had. We will also be sharing some exciting news about our upcoming bioprocessing webinar series launching in October later this year. Thank you for listening and enjoy the rest of your day. Thank you very much.
Well,